Picture this. You're out in the garden, watering the lawn, and you just need the water to reach a tiny bit further. What do you instinctively do? You put your thumb right over the end of the hose. But have you ever actually stopped to wonder why water sprays so much faster when you pinch the hose? I mean, you cover a portion of the opening with your thumb, and suddenly the water just shoots out with way greater velocity. It honestly feels a little bit like magic. But actually, it's a profound, universal lesson in physics hiding right there in your own backyard. Welcome to This Explainer. Today, we are going to completely unpack the incredible physics behind that everyday garden hose. We're looking at continuity and the conservation of mass. We're literally going to see how a massive, unbreakable law of the universe translates directly into how fluids behave all around us. Here's our roadmap for today. First, the universal rule of mass. Second, where does water go? Third, deriving the continuity equation. And finally, calculating real river flow. Section 1. Universal law of mass. The fundamental law governing everything. So here is the formal definition. The law of conservation of mass states, for any system closed to all transfers of matter and energy, the mass of the system must remain constant over time. And I really want you to focus on that phrase right at the end, must remain constant over time. That is the absolute anchor for this entire explainer. Okay, let's dive into this and break that grand definition down into 3 specific, inescapable rules. Number 1, a closed system's mass absolutely cannot change. 2, this means quantity cannot just be added or removed arbitrarily. And 3, mass can neither be created nor destroyed. It can only be rearranged in space or changed in form. Basically, the universe keeps a super strict, unyielding accounting of every single atom. Moving on to section 2, where does water go? Taking these universal laws and applying them directly to fluid dynamics. Check this out, because it brilliantly illustrates the connection. The real-world hand pinching the hose acts exactly like a scientific pipe that's suddenly narrowing. In the wider section, the water moves a bit slower, but in the narrowed section, it moves much faster. So why exactly does it speed up? Well, it really all comes down to this brilliant, completely common sense quote, the water all has to go somewhere, right? You aren't creating new water with your thumb, and you definitely aren't destroying it. You're just forcing the exact same amount of water through a much tighter space. To put that into strict scientific terms, the rate a fluid enters a pipe absolutely must equal the rate the fluid leaves the pipe. There can't be any hidden sources creating fluid magically out of nowhere, and there are no invisible sinks making fluid permanently disappear. What goes in must come out at the exact same rate. All right, section 3, deriving the continuity equation, unraveling the math of moving fluids. Imagine fluid flowing from a wider area 1 to a narrower area 2. It's kind of like a giant puzzle. We're going to track a small chunk of fluid over a very short interval of time, and we'll track its velocity, which is v, and the cross-sectional area of the pipe, which is a capital A. Let's walk step by step through calculating the mass flux down at that lower, wider end. First, the distance the fluid covers is simply its velocity multiplied by our tiny time interval. Second, to get the total volume of that chunk of fluid, we just multiply that distance by the cross-sectional area, A1. Third, to find the actual mass of the fluid, we multiply that volume by the fluid's density, represented by the Greek letter rho. And finally, to find the mass flux, which is simply mass per unit of time, we divide by time, leaving us with our starting density times our starting area times our starting velocity. And here is the big payoff. Because the flow is steady, what enters the lower end must exactly equal what exits the upper end. We just set them equal to each other. So density 1, area 1, velocity 1 perfectly equals density 2, area 2, velocity 2. And there it is. This is our foundational continuity equation. Now for a general, compressible fluid like a gas, you absolutely have to use the full equation with density. But here is the massive twist for incompressible fluids, like water. Because water basically cannot be compressed, its density remains completely constant from one end of the pipe to the other. That means density cancels out on both sides completely. We literally just drop it entirely, and we're left with this beautifully simple equation, A1 times V1 equals A2 times V2. Area times velocity in equals area times velocity out. Section 4. Calculating real river flow, applying the equation to an actual real-world problem.
Let's set the scene with this specific scenario. We've got a river flowing along. Initially, the river is a nice, wide 40 meters across, but then it squeezes down into a very narrow gorge that's only 3.7 meters wide. We need to figure out exactly how deep that narrow gorge is, based entirely on how the water behaves as it speeds up. Now, what's really interesting about this slide is how we organize our raw data before calculating that mysterious depth. Over in our knowns column, the initial river has a width of 40 meters, a depth of 2.2 meters, and a leisurely velocity of 4.5 meters per second. The gorge has a width of 3.7 meters, and the water speeds up significantly to 6.0 meters per second. Over in our unknowns column, we just have one single missing piece, D2, the depth of the gorge. To solve this, we take our beautiful simplified continuity equation and just expand the area part. Instead of a generic area, we write area out as width times depth, so it fits our rectangular river. So the first area times velocity becomes width 1, depth 1, velocity 1. And we set that perfectly equal to the gorge with 2, depth 2, velocity 2. We do a little rearranging to solve for depth 2. Plug in our numbers from the table, and boom! Our final answer is exactly 18 meters. The river absolutely must carve out a depth of 18 meters in that narrow gorge just to handle the exact same volume of water rushing through. The continuity equation works perfectly, proving once again that mass is always, always conserved. So, as we wrap up this explainer, I want to leave you with this to ponder. If that river gorge were even narrower, say just 1 single meter wide, how incredibly deep or how dangerously fast would the water have to flow to obey the fundamental laws of the universe? Next time you pinch a garden hose, remember, you aren't just making a temporary sprinkler. You are literally holding the immense, inescapable laws of physics right at the tip of your thumb. Thanks for joining me on this explainer, and keep questioning the mechanics of the world around you.